Okay, so we're taking a look at some Octave Online stuff here, and I've got the windows resized here so we can take a look at the SVD, this expansion that I wanted to consider today. And there are two things that I wanted to look at today. One of them is the SVD, but the other is to take a look and see what a MATLAB data file looks like. And so I've got this selected here, clowndata.mat. Uh, you can tell it's a MATLAB data file because it ends in an MAT. And that file is a binary file, so you're not going to be able to see anything if you click on it or try to open it. Um, and so we're not able to do any kind of interactive editing of the file. I will put that on our class website so you can download it and save it on your home computer and then upload it. Drop your file here in the Octave online screen. There's a different way to do it in Python that we'll talk about. Okay, and so I'll probably just have the image available in Python without the color map. That's probably the easiest way to do that. Okay, so what's going to happen now is we want to load the data, and so this is true whenever you load a MATLAB data file. You can just load the file name without .mat if you want. I don't think it actually matters if you do include the MAT. Nope. But that's sometimes shorter, and you'll see that there's a couple of variables there. I don't really like this variable panel here. I like to see what's going on, so I type in WHOS, and that lists the variables that I have. It also tells me their size, which is kind of nice. So this image of a clown actually is what it is. Comes in a matrix X, and then map whatever that is, 81 by 3. And so if we take a look at X, we'll take a look at the first 10 elements. Oops. First 10 rows, first 10 columns, just a 10 by 10 the initial 10 by 10 submatrix there. You can see that X is actually just a bunch of integers. And those integers are going to run from minimum X to maximum X, 1 to 81. And that's not a surprise. Our map is 81 by 3. And so let's take a look at map and see what that is. So you can see that that's a bunch of numbers between 0 and 1. And so the first column is the red column, and then the middle column is how much green, and then the last column is how much blue. So this is the red, green, blue version of a color. Okay, so the closer to 0 you get, the darker it is, and in fact 0, 0, 0 is black. Okay, and so if we look down here, and if one of the X value, oh, where's my X values? There they are. If one of my X values here was a 1, that would correspond to black. This is 2 here, so there's a little bit of red, right? Green, blue. There's no green, no blue, so this is a little bit of red, and it's a dark red. So kind of a really dark red is that first row here. Okay, and so that's what the numbers represent, and in fact that's common with an image. This is called an indexed image, where you've reduced the number of colors. This only has 81 colors in it, and so the image isn't very complicated. Other images are typically, there's 3 matrices attached to each image, and each of those numbers in each matrix runs from 0 to 255, and those represent the amount of red, green, and black in each of those panels. And so usually you'll have 3 arrays or 3 matrices attached to one image, and we'll see that later on. For us, this is an indexed image, so we only have a single matrix and a color map that goes with it. So it's very much like color by numbers. All right. So to see the image, we can type in image and X. Oops. You know what? I should have redid my color map, because this color map is already there. When I cleared the I did this once before. Um, yeah, it looks like the color map has always been there, but yeah, I had to tell Maple or MATLAB what the color map was. So the way to do that is color map. In fact, if you do help color map, you can see what the other color maps are. There's a bunch of different color maps you can use. Um, the default is Veritas, and so usually, if you change it back to default, Veritas, yeah, that's usually what you would see the first thing, and so we would change it back over to color map. Good, and now we see it in the right color. Very good. Okay, so now those are images and MATLAB data files. Now I want to take the SVD and see what the SVD tells me about this image. I'm just going to go ahead and take the full SVD. Okay, so let me see what the matrices look like here. And so the thing I want to look at first is the matrix S. That's sigma in the SVD, and you remember that sigma is a diagonal matrix. It's not square, but it'll have the values of the singular. I shouldn't have said it that way. I should have said it's the singular values, not the values of the singular uh, of the matrix. Okay, it's getting late today. I've had a long day. So I can change the matrix to a vector. S equals diag capital S, and now little s will just be a vector values, and so it's hard to see in that way. Let's plot them. So these are our singular values, and so you remember what we were talking about before when we were talking about trying to find the rank of the matrix. Yeah, what's the rank of this matrix? So typically you would try to look to see if there's a gap here, where the singular values just immediately drop to 0. But you see what's happening here is this exponential decrease down here. That's really a kind of a typical scheme that you see for the singular values of a matrix, a big matrix like this. And so let's go ahead and plot the log of S maybe, just so we can get a better picture. Yeah, and so you can see here, right, that the rank is just about 200, like 199. Looks like the last value is a little funky, and that's pretty common. So in this case, if we ask MATLAB what the rank is, yeah, it's full rank for MATLAB. So I wonder if we need the matrix to be full rank. By that I mean the SVD down here, what you're seeing down here, is actually an approximation to the matrix, and it's a rank 1. So each of these, think of A as being the image of the clown, and I'm decomposing it into a sum of simpler images. Each of these has rank 1, right? And so the question is do I need all of these rank 1 matrices to make up the clown, or can I stop it early and still get a clown out of it? And so let's try it. I'm going to do a little bit of coding here. So let's try a rank 5 approximation first. And so we'll say partial reconstruction is equal to rank 5. I'm going to use n here, so next time I can just recall this. I don't need to do all this typing. I can just change the value of n, and I'm just, again, this is a rank 5 approximation to the image. Don't forget your semicolon or you're going to get lots of stuff coming out. Okay, and now we'll do an image of the partial recon and see what we get. Oh, you can already see a clown, right? That's only a rank 5 approximation, and you can already see a lot of the big details coming out. So we can do more. So maybe a rank 10 approximation, and we'll do an image of the partial recon. Oh, why is that taking so long? Did I mess something up there? It shouldn't have been taking that long. Oh, there it goes. That is the rank 10 approximation. Okay. Um, I'm not sure why that happened, but let's keep going. So maybe let's see what happens with a rank 50 approximation. Did that finish this time? And then image, partial recon. There we go. That's a lot faster. Good. And now, gosh, that's a nice image of the clown. You can recognize it and everything, right? So now, what happens if we compare the partial or the actual matrix X? Again, just as a reminder, that was X 1 to 10, 1 to 10, right? 10 by 10 subarray. With the partial recon, we can kind of see how fat or how close we are. I'm not sure if that's going to show up all very nicely. Nah, not very nicely. Maybe I'll say formats, bank. That will reduce that a little bit. There we go. That's easier to see. How does that compare with the original 1 to 10, 1 to 10? Can we see them both there? Oh, there we go. Ah, you can see that they are fairly close, right? And in fact, if I took this original matrix and I rounded off the numbers, it'd be really close, right? So in fact, if I do an image of a round partial recon, that's even going to get closer, right? Well, I can't really tell too much. Okay, but you can see, right, with a rank 50 approximation, we're really close to the original matrix. And so if we don't need the exact data, if we just want an approximation to the data, then the SVD may be able to give us a good approximation. Now notice I should say that the singular values that you're looking at down here, the sigma 1, sigma 2, sigma 3, and so on, those are ordered from highest to lowest, right? And so there is an ordering to this. And so when we talk about when we talk about statistics a little bit, we'll see what these sigmas actually represent in terms of stats. Okay, and so we can also see what's left over. So if I take a look, let's use the line up here with an N in it. There it is. I'm going to take a look at what's left over. So what is the let's see, I'll take 51 and we'll say leftovers, or just leftover, is the matrix from M to N, and just go ahead and put that in for each one. I guess I could have defined this, well, you know what I'm talking about. Image, leftover. Okay, that you can't really see very much there, so you can scale the image by image scale leftover. Leftover. Good. And so now you can see what's left over, what's missing in the image really isn't very much. And just to do a reality check here, if we take partial recon plus leftover, we should get the original image. Yep. We're getting a little bit of funk here. Is that due to round off error? Probably. Because we're not really looking at the original. Let me round that off. See, do you think it's going to get rid of the funk? Yeah, it did get rid of the funk. Okay. So now the clown looks better. Doesn't have that weird stuff on there. Okay, so you see that you can decompose a matrix very nicely using the SVD, and you can get a rough approximation to the image. You know, a low rank approximation to the image by using the SVD. So I'm going to let you practice on a different image, and then we're going to talk a little bit about some statistics after that. So I will see you later.